Assalamu alaikum wa rahmatullahi wa barakatuh. I am Engineer Haytham Al-Hazmi. I will present you with the basics of analog to digital converter errors. I would like to start an introduction about the analog to digital converter. Imagine you have a temperature sensor that is reading the temperatures from 0 to 100 degrees. The temperature sensor, let's say, for example, it will transform these readings between the 0 to 100 degrees to a range of voltage between 0 to 10 volt. So that the 10 volt would equal the 100 degrees, and the 0 is for the 0 degrees, and everything in between. So this analog reading cannot be read by the DSP or micro C or FPGA. It has to be transformed to a binary number, so it can digitally processed. So for that we have the ADC, which will transform this analog reading to number of levels as a binary numbers. The 0 representing the zeros of the binary number. The maximum number, which is in this example is 10 volt, will be represented by the all ones binary number. So to find this value from the input that we have in the ADC, we have this equation that can be used to calculate how much is the value here. So let's say, for example, we have an input voltage of 3 volt inside this range. Then we will say the 3 volt here multiplied by 2 to the power of the ADC resolution. Normally the ADCs are between 8 bits to maybe maximum 24 bits. So let's say here in this example 16 bits. Then the output would be 16 bits that is representing the analog range here. So 3 by 2 to the power 16 divided by the range that we have, which is 10 minus 0 here. Then rounding this value will give us the number 19660, which is in binary number like this. So the DSP or micro C FPGA will read this binary number. Then inside the controller here, it will be calculated reversibly to find the actual voltage that it has in the first input here. Let's see an example here for how does the ADC works with the analog input. Like we have this input voltage, which is analog. The ADC actually is dividing the readings to a number of levels. So the analog input, if it is between any of these levels, it will be read as one value, as called one LSB. So inside this range, we will have only one LSB. We don't have anything more or less. And inside this range, we'll have two LSB. Inside this range, we'll have 3, 4, 5, 6, and 7. This is an example for an ADC of 3 bits, which I don't believe it exists. 3 bits is a very low number. So the one LSB, how much does it equal in voltage? The equation is that the input voltage range that you have in the ADC, which or what the ADC is capable to. In our previous example, it was 10 volt. Let's say here it's for 10 volt divided by 2 to the power of 3 bits in this for this graph. Then every LSB will be 1.43 volt. So taking minus 0.5 LSB and positive 0.5 LSB, we will have the range of 1.43 volt minus 0.71 volt and plus 0.71 volt. So any readings inside this range it will be considered as 1 LSB. And every multiplication of this range will be a 2, 3, 4, 5, and so on. The ADC actually is reading the input, the analog input, at samples. So it has a sampling rate that the ADC will not read anything between the two times of the samples. Like for example, if we have an ADC with 1 kilo sample per second, then we will read every 1 millisecond only. And anything in between the 2 milliseconds will not be read. Like here, for example, like we have a high analog input, but it is not at the point of the sample time. So it will not be read here. Until it reaches to the sample point, then the true reading will be 2 LSB from the ADC. Even here, we didn't take all the values here because it is still did not reach at the sample time, which is here at 5 LSB, and so on. Despite that, the ADC have many kind of errors. In this presentation, I'm trying to show what are these errors in brief presentation. I would like to start with the offset and gain errors. The offset error, it's like we have here the blue line, which is the ideal line, the ideal reading. This is the true readings, the actual reading that we want to read. The offset error, it will be an increase for all the readings, like a positive or a negative offset. Also, we have the gain error. The gain error is a scale factor or a multiplication on the readings. So the difference between the actual reading and the ideal reading will be increasing as the number is increased, or decreasing as the number is decreased less than 0. Also, we have the DNL, or the differential nonlinearity. The DNL is measuring how much is the maximum 1 LSB trying to read a voltage. Like in the ideal case, that every LSB will read the same voltage, but at some points we will have an LSB that's reading more than the voltage that the ADC is supposed to read. Like let's say, for example, if we have an ADC with 1 microvolt LSB, some points like maybe it will be 1.2 volt, 2 microvolts, which will be considered as a DNL error. So if the number of the DNA was more than 1 LSB, then we will have a missing code problem, that this code will not be seen any time of trying to read the ADC or at any sample. Another error is the INL, or the integral nonlinearity, which is how much is the maximum distance between the ideal reading and the actual reading because of the DNL. We said that the DNL it shows that it is not exactly one LSB for every reading. So if we have many DNLs in many places of the ADC codes, then the result of this number of DNLs will give us an INL of how much is the distance because of the DNL between the ideal reading and the actual reading. I would like to show the signal to noise ratio, or SNR. So the readings in the ADC is including the true signal, which is coupled with a noise generated from the ADC itself. So it is not a pure reading. No, it have a coupled noise that we are trying to get rid of it. The SNR is actually calculated by finding the RMS of the signal and the RMS of the noise, taking the 20 log of the division between the two RMSs. We will have a dB reading which explain or express the SNR in dB. For that, the engineers have calculated an ideal value for the SNR according to the resolution of the ADC. So it would be 6.02 multiplied by the resolution of the ADC plus 1.76. This should be the ideal value that you must have in your ADC to have a very clear readings. This is a table showing a different ideal values of SNR for different resolutions. For example, for the 24 bits, the ideal SNR would be 146 dB, and so on. From this SNR, or the ideal number of SNR, engineers have calculated the effective number of bits, which is the SNR number, the actual SNR number, not the ideal. I mean the SNR, as actual number in the ADC, minus 1.76 divided by 6.02, to get how much is your ADC has an effective bits. It's called an effective bits because the other numbers of bits are noisy. So I can't depend on them. I can't depend on them as an actual readings. But the effective number of bits are fixed when the analog inputs is fixed and as a true value. This is an example showing a different effective number of bits for different ADCs from analog device actually. Like for example, the ADAQ of resolution 18 bits, it has an SNR with 100 dB. Then for this SNR, we will consider the ADC as a 16.32 bits, not as an 18 bits. In this case, that if we did not use a filters or any digital processing to get a better results. So if we are using the ADC itself without filter, without digital processing, it would be a 16.32 bits, not 18 bits actually, and so on. Thank you for listening. I hope it was an informative presentation. If you have any question, please leave me the question in the comments and I will be answered as soon as possible.